Hello, today we're going to talk about Gibbs free energy and thermodynamic favorability. So Gibbs free energy is the energy that is available to do work. All right. We use delta G to represent Gibbs free energy, or the change in free energy. And if you have a delta G that is positive, that means that the process involved has to absorb free energy, or use free energy. And when you have a negative value for delta G, it releases free energy. So when we have something that is releasing free energy, that is what we call thermodynamically favorable or spontaneous. Now the AP exam has kind of moved away from using the word spontaneous because it can be confusing based on the colloquial meanings of the word. So I'm going to try to stick to thermodynamically favorable as much as possible, but spontaneous might slip in sometimes. Let's look at an example with just a phase change first. So let's say you have water, okay, and you have water at two different temperatures, liquid water at two different temperatures. And let's say you have it at negative 5 degrees Celsius and you have it at 5 degrees Celsius. At negative 5 degrees Celsius, that's below water's freezing point. So the water wants to freeze and wants to turn into a solid. And it will do that without any input of energy from an outside source. So we would call this a spontaneous process when it freezes. I use spontaneous again, a thermodynamically favorable process, because it just kind of happens. And so it will release free energy. It will have a delta G that is negative. But if you have water that's above its freezing point, 5 degrees Celsius, it doesn't want to freeze. It's not going to freeze unless you do something to it, like increasing the pressure. So we would say that that's not thermodynamically favorable or non-spontaneous. And its delta G is positive. So that's an example with a phase change. Here's another example. Let's use a chemical reaction. Hydrogen peroxide will decompose into water and oxygen gas. Okay, and it just does that. You don't have to do anything to the hydrogen peroxide. It just will break down into water and oxygen gas. It does it kind of slowly, but it's why we keep hydrogen peroxide in brown bottles, to prevent the light coming in and increasing the speed of that decomposition. But the overall reaction is spontaneous. It's thermodynamically favorable. It has a value of delta G that is negative. The reverse reaction, the water and oxygen gas forming a hydrogen peroxide, is not thermodynamically favorable. You have water vapor and oxygen gas hanging out in our air all the time, and it doesn't spontaneously just produce hydrogen peroxide. So its delta G is positive, is not thermodynamically favorable. So just a quick reminder, enthalpy is delta H. It has to do with the heat involved. If you have an exothermic reaction, that tends to be more favorable, thermodynamically favorable, and so delta H is negative. And an endothermic reaction, that tends to be less thermodynamically favorable, and it's a positive value of delta H. Delta S, the entropy, if I have more disorder, entropy is positive. That tends to be more thermodynamically favorable. If you decrease the disorder, that tends to be less thermodynamically favorable, and delta S is negative. Both of these things, enthalpy and entropy, they both affect Gibbs free energy, which is delta G. So again, if you're looking for a spontaneous process, a thermodynamically favorable process, exothermic reactions and reactions that increase the disorder will tend to make delta G more negative or more spontaneous. And we'll look at the mathematical relationship in just a minute. The more you have endothermic processes and you're decreasing the disorder, the more delta G is going to be positive. But both of those things affect it. So it is definitely possible that you have something that's exothermic and decreasing disorder, but the reaction is still spontaneous. It's also possible that you have something that is endothermic and you're increasing the disorder of the reaction and still have a spontaneous process. So we're going to look at how we relate that and figure that out mathematically. So here's our mathematical relationship. Delta G is equal to delta H minus the temperature times delta S. The biggest thing, and I've been trying to point it out as much as possible, but delta H is typically given in kilojoules per mole. Delta S, for some reason, they give it typically in joules per mole Kelvin. That means you have to convert it into kilojoules per mole Kelvin before you can plug it into this equation. All right. Because your delta H is in kilojoules, you need the delta S to also be in kilojoules. That way, when you solve, this is your temperature in Kelvin, the Kelvin temperature will cancel out, and you're subtracting the same unit for your enthalpy and entropy, and you'll wind up with your unit for free energy is kilojoules per mole. So please make sure that you pay attention to those units. So that is our overall mathematical relationship. You definitely will be asked to plug in values and solve for delta G. And then a lot of times the follow-up question then is the process thermodynamically favorable? And if you have delta G is negative, yes, it is thermodynamically favorable. If delta G is positive, no, it is not thermodynamically favorable. So there's a quick shortcut you can use to just kind of estimate the thermodynamic favorability. They will ask questions about this kind of shortcut, but it's just based on the sign of delta H and delta S. Delta H, delta S. Okay. So if you have a reaction that is releasing heat energy and becoming more disordered, both of those things are thermodynamically favorable. Your delta G will be negative always. It's always thermodynamically favorable overall. Now, if you have an endothermic reaction and it's decreasing disorder, both of those things are not favorable. So delta G will always be positive. It will always be not thermodynamically favorable. I'm going to write it like this. It will be negative delta G never. It will never be thermodynamically favorable. Now, if I have a negative enthalpy, it's exothermic, but the entropy is decreasing, delta G will be negative at low temperatures only. That's because of our mathematical relationship here, delta G equals delta H minus T delta S. If delta H is negative and delta S is also negative, a negative times a negative makes positive. So if this whole thing is positive, we need this to be small enough that it doesn't overpower the negative from the delta H. So if you have a low temperature, it makes this term lower overall, indicating that you will have a negative value. Now they could ask, what temperature does it become spontaneous? So then what you would do is you would plug in 0 for delta G, you plug in your delta H and your delta S and solve for T. And any temperature below that, in this scenario, would be spontaneous. And then our last option is if you have an endothermic reaction, but it's increasing in disorder, it will be spontaneous or thermodynamically favorable at high temperatures only. Let's look at that relationship again. Delta H is positive, delta S is positive. This whole term here, right, is positive. Okay, or if you think about it, the positive value, you're subtracting the positive value here, or you could say this whole thing is negative overall, however you want to think about it. But essentially, we need this whole thing to be large enough so that it overpowers the positive value from the delta H. So as long as your T times delta S is bigger than your delta H, then delta G will be negative. They could also ask you in this scenario what temperature it becomes spontaneous. So you would plug in 0 for delta G your positive delta H, positive delta S, and you'd solve for temperature. Any temperature above that would be spontaneous. So this is, again, kind of a shortcut. If they don't give you the values, or if they're asking you about what's temperature, you can kind of figure out based on this pattern. Definitely know the pattern here. The last thing they might ask you to do is give you the free energy, the absolute free energy values for different substances, and ask you to find the overall Gibbs free energy for a particular process. And this equation is going to look really familiar. Your standard change in free energy is going to be equal to the sum of the free energy changes for your products minus the sum of your free energy changes for your reactants. Reactants. There we go. Now, just like with delta H, these values are going to be formation values. So I didn't really leave a lot of space in there, but so they're delta GF, they're formation values. So that means if you have an element in its standard state, it will have a Gibbs free energy value of 0. But for the most part, you're just going to do the products, add them all up, use the coefficients, minus the reactants, add them all up, use the coefficients. And that will give you the overall free energy change for a particular process. Let's look at a couple examples. We already talked about this one. The decomposition of hydrogen peroxide occurs slowly at room temperature. Predict the sign for delta G and justify your answer. Anytime you see something that says it occurs, even if it's slow or fast or whatever, it doesn't matter the speed. But as long as it is occurring without outside work, delta G will be negative because it's thermodynamically favorable. And then for delta S, that's entropy. It's going from 2 aqueous particles into 3 particles, and one of them's a gas, so entropy will be positive. Here's another reaction they give us, and they want us to calculate the value of delta G. And they give us some of these delta G formation values, and notice that the elements in their standard states have a value of 0. So what you'll do is the products. So you'll do the 2 times the value for water plus 4 times the value for CO2. And then nothing for the nitrogen because it's 0, minus the reactants. So 4 times the HCN is 121, and nothing for the oxygen because it's 0. So when you solve that, you get negative 2,536, and that's kilojoules per mole. And so yes, the reaction is thermodynamically favorable because it is a negative value. Here's one more reaction, our theoretical reaction, A plus B yields C plus D. They give us delta H, delta S. Is this reaction thermodynamically favorable? Let's look at just the signs here. So delta H is negative, that's favorable, it's exothermic. Delta S is negative, it's getting less disordered, that is not favorable. So because they're both negative, it will be spontaneous or thermodynamically favorable overall at low temperatures only. Okay. So let's see if 298 is a low enough temperature by plugging it into the equation. Delta G equals delta H minus the temperature, which is 298, times delta S. But remember that your entropy must be changed to kilojoules. So times negative 0.0042 kilojoules per mole Kelvin. So be careful with that. When you multiply and you subtract, you find that delta G is negative 22.8 kilojoules per mole. And that's negative, so yes, it is thermodynamically favorable at 298. That temperature is low enough that the reaction is favorable.